So welcome back to the second hour of the morning. We're happy to have Sara Billey telling us about quilts of alternating finely.
Thank you, and thank you to the organizers, Paolo, Dave, Leo, and Junie. But it's such a great audience to put together and great reason to come together. So today I'm going to talk about some work that's joined with Matthias Konvalenka. This is based on a paper that we posted in the archive in December, so you can look it up if you'd like to. The title of the workshop is Combinatorics of Enumerative Geometry, and that's very close to enumerative combinatorics inspired by geometry, which is what this is, but maybe this is a slightly different flavor, what you're expecting. But hopefully you're the right audience to target, because we do need more geometry to go with the enumerative combinatorics that we've been working on. And it was inspired by geometry. So here's the plan. I want to talk to you about generalized rank functions. And those are going to become the quilts, ASM quilts. And then the quilt lattice comes with two posets, P and Q. And then we'll talk about some enumerative results and quite a few open problems that are left in this area. So to begin with, there are lots of rank functions in the world, you've probably noticed. For example, there are rank functions on posets. If you're lucky, you have a ranked poset. So I'm only going to deal with posets that are always finite and always have a unique minimal element 0 hat and unique maximal element 1 hat. If I need to differentiate between different posets, I'll put a sub P on the minimal and maximal elements. And in this case, a poset is ranked if and only if every maximal chain from 0 hat to 1 hat has the exact same length. And if you have that nice property, then you get a rank function that goes with the poset, and it's determined by just, first of all, the rank of the minimal element is 0, and then every time you step up by 1 with a covering relation, if Y covers X, and there's nothing in between, that's what covers means, then the rank function steps up by exactly 1. So this is a recurrence that would give you the entire function. I'm going to use this notation X less than dot Y to mean the covering relations, okay? And there are lots of ranked posets, finite ranked posets that have a unique minimal and maximal element. Here's 3 examples. And these will be a theme throughout the talk. So let me define the notation here. So if you just take an antichain, so let's say J elements which are not related to each other at all, and you append a 0 and a 1, we'll call that the antichain poset. And so let's denote that by A sub 2 of J. J is the number of elements in the antichain. Or you could have the Boolean lattice, that's just the subsets of the numbers from 1 to n ordered by inclusion, B sub n. And another one is just the chain and elements that are totally ordered. Actually, I would kind of like to call this n plus 1 elements that are totally ordered. So that 0 is the minimal element, and then n is the maximal element. So Cn has n plus 1 elements. Okay, and all of these, the subscript is the rank of those posets. Okay, so those are some examples. But also matrices have ranks, right? And we use this all the time with Schubert varieties. The rank of a matrix, of course, is the dimension of its column span or the dimension of its row span. And one nice thing about it, this function, is if you can extend it to all of the submatrices of a matrix too, and there's some coherence to these different ranks. So I could think of the rank sub m as a function on subsets cross subsets, right? Subset of the rows cross subsets of the columns. And you can think of all that data at once, the ranks of all of those things. And what are the properties of those kinds of functions? Well, they're going to be bounded. So if you have a k by n matrix, let's say to start off with, then the rank of any submatrix is between 0 and whatever the minimum is, k or n. And also you could even say that it's the rank of this particular submatrix ij is going to be less than or equal to the minimum of the size of I or the size of j. So they're bounded in some sense, and they exhibit this phenomena of Boolean growth. So Boolean growth is the key player here. So this means that if you compare the rank of one submatrix and you add exactly 1 row to it or 1 column to it, the rank can jump up by at most 1. It'll either jump by 0 or it'll jump by 1, and there are no other choices. That's the Boolean 0 or 1. Okay. Okay, so we kind of think of this generalized rank function, given a certain matrix, is a function on the product of two Boolean posets, BK cross BN. Right. Okay, and a key player for the conference is matroids. So I'd be neglected if I didn't talk about ranks of matroids. So as you know, among the many ways that Federico mentioned that we should think of a matroid is the set of numbers from 1 to n. And then you have some sets that are the bases for this matroid that are given to you. They all have to have the same size, whatever that size is. That's the rank of the matroid. And you can also extend the rank function to any subset of the numbers from 1 to n. Every subset of numbers that are contained in some base will be independent. So among a subset, let's call it A, of the numbers from 1 to n, there is a unique size of the largest independent subset in there. And that'll be the rank of A in this matroid. Okay, so what are some properties of ranks of matroids like this? You can think of this rank function then as a function from the Boolean lattice Bn to the chain Ck, if you'd like. Right, and it's going to be bounded. The rank of a subset A is between 0 and the size of A. It's going to be the size of the largest independent set. It's got this monotonicity property that the rank of A is always less than or equal to the rank of B if B contains A. So it grows monotonically as you go up a chain in the Boolean lattice. And it's got this nice submodularity property. So that means that the rank of A union B plus the rank of A intersect B is less than or equal to the rank of A by itself plus the rank of B by itself. All right. So a nice theorem, or could take it as the definition of a matroid, is that any function at all, let's call it R, from the Boolean lattice to the chain CK, satisfying these three properties, determines a matroid. This could have been on Federico's list, but I don't think it was there. This is my favorite one. So, but there are many different ways of defining a matroid. And how do you go from such a rank function back to a base, a list of bases? Well, that's very easy. The bases of a matroid given by such a rank function would just be the subsets. This notation n choose k like this means the subsets of size k of the numbers from 1 to n. The subsets with rank exactly equal to k. And how do I know I have some? Maybe there's none. Maybe there's no subsets that have rank k. Well, I know that because the function is required to be surjective. Okay. I just want to take a note that if you have the monotonicity property and you have the submodularity property, then you do have bounded growth. You can figure that out. You're certainly going to be increasing if you have the monotonicity property, but you also can figure out that you grow by at most 1, because if you take B to be just a single element that is not in A, then its intersection would be 0 here. And then you have to work out that the rank has to be exactly 1 more. Okay, so bounded growth also happens with these rank functions of matroids. Okay, so we were inspired by looking at spanning line configurations that were studied by Pawlowski-Rhodes, and I've talked about that recently from the Schubert seminar and other places. And we have some need to understand rank functions like this, particularly from CK cross BN to CK. And so we started thinking, well, maybe we need more than BK cross BN and CK cross CN. Maybe we need to think about rank functions for all pairs of posets P and Q, much more generally than we were before. So this is definitely motivated from the geometry, starting from Schubert varieties and building up, but now incorporating something bigger. So, like I said, always the posets are going to be finite ranked and have a 0 and a 1. So let's say P and Q are 2 posets like that. And this is the key definition. So take a picture or write down whatever you need to do. A function f from P cross Q. The poset, does everybody know what it means to take the product of 2 posets? You just sort of take one of the copies of posets, replace every element by the other one, and then the implied edges kind of go along. So it's a function from P cross Q to the natural numbers such it's going to be an alternating sign matrix quilt, ASM for short, if it has these three properties. So f of x, y equals 0 whenever you're at the boundary condition at the bottom. So if either x is the 0 of p or y is the 0 of, y is the 0 of q. And the other boundary condition is at the top. Once you get to the top of p and the top of q, then this function must be equal to the minimum of the rank of p or the rank of q. And the Boolean growth function still has to follow. So if you take the difference between f of x prime y prime and f of x y, it'll always be 0 or 1 if you have a common relation in the product of posets. All right, and the set of all such functions, we'll call those the quilts of p and q. So this is the key definition, and so you have to refer back to it. I put it there too. It's a simple enough definition, right? So what do these?
Question. So when you say x comma y is covered by x prime comma y prime, in that x should be covered by x prime and y should be covered by y prime?
Not quite both. Actually, do it the other way. So either x is covered by y prime and y is equal to y prime, or the other way, x is equal to y prime and y is covered by y prime. Those are the only two kinds of cover relations
Okay, thanks.
in the product poset.
Because
So we're either sort of stepping up this way or we're stepping up that
I
way.
thought you were using it in the other way with the, when you had I and j columns, rows. But
Well, in that case, I was adding either one extra column or I was adding one extra row. Oh, it doesn't matter because I just care about the rank first.
Sorry.
So nothing squared here necessarily. Mhm. Yeah, okay, good. So what do these things look like? You know, this is a lot of data, right? You don't want to have to write down a big one, but here's a small one. Let's take B3 cross C2. All right, we're gonna look at a quilt on there. So I think about B3 always sort of organized like this. And C2 will be my chain with 0, 1, 2 at the bottom. So I take a copy of B3 and I make 3 copies of it because C2 has 3 elements and they're kind of going up like this. And now I start filling in, instead of these labels of what the elements are, you just remember what they are over here, start filling in the numbers in this. So on the boundary, I have to have zeros at the bottom, right? So 0, 0, 0, but also on this whole first copy, I have to have 0. At the top, I have to have 2 because the rank of B3 is 3 and the rank of C2 is 2. 2 is smaller. So I have to get up to 2 in the end. And I have to step along by at most 1, right? So there are some forced implications in this picture. You see what's forced? A couple of them are forced. Yeah.
The 1 on the top of
You gotta
the.
have a 1, yeah. And then once you have a 1 there, right, I'm gonna have to get from 0 to 1. Now I have a lot of choice how to do that. Mhm. But you can fill it in now in a couple of different ways. So let's say I put in the next row here underneath the 2. Since I have a 2 here on the right, I kind of have to get up to from 0 up to 2. So this one would have to be 1. And this has to be true for everything that 2 covers. So this also has to be a 1. And then I have a little choice here. Maybe I'll make that a 1. And maybe if I put in a couple things over here, the last one I just filled in there, that has to be a 1 also. Once you have a 2 here, then that implies that you have to have a 1 here in order to make it reach. Okay, and now underneath the 0, I have forced zeros. And then I have another choice, but just for fun, let's make it 1. So there's an example of a quilt. Okay. Some data is forced, some data is free. All right, so I don't want to have to write this out every single time, especially when I have a chain, I can kind of collapse things down. So since the chain is so nice and linear, I can start to think about these 3 zeros at the bottom as just 0, 0, 0. And then looking in each entry, what happens on all 3 levels, I can make a sequence of 3 numbers that go with each. So a little bit more compressed way to write down that data would be something like this. In the case when you have one of them is a chain, it always makes sense to write your poset, just make the poset, whatever the Hasse diagram is, and then in every entry, I have to have a weakly increasing sequence. But then they have to have a coherence property as you go up and down too. Right, so that you make sure you're stepping up by one or zero. All right, and then here's another example, simpler case even actually. So let's say you have the product of two chains. Then one of these quilts is just going to be a, right? It's going to be a matrix that has zeros on the left column and the bottom because of those boundary requirements. It's going to get all the way up to whatever the minimum rank is. And in between, I have to step up by monotone, by this, sorry, Boolean growth. So these look like Southwest rank tables or permutations, right? Except that there's more of them than that. Those are special kinds. And I'd like to compare this kind of a table with an alternating sign matrix, which is a friend of ours too. So how do you go from one to the other? Well, looking at any little 2x2 square, this is the trick to go from corner sign matrices to alternating sign matrices. You take the northwest corner, subtract off the two, the northwest, southeast corner, and then add in the other one, sort of as an inclusion exclusion thing. And then we go from the first to the second matrix. If you haven't seen alternating sign matrices before, these are nice. They're 0, 1, -1 matrices. And they have the property that among the non-zero values, they have to alternate between 1, -1, 1, -1. And they always do have to have a 1 for, as you read from the left first. They also, since they're not square necessarily, they have to have a 1 from the bottom up, but not necessarily at the top. And then there's a little extra requirement, so I'll get to the formal definition, but let me point out this intermediate fact. And that is anytime you have a function from CK cross CN to the natural numbers, such that it has the boundary conditions that we had before and Boolean growth, this will always be a corner sum matrix, and it will always have a corresponding alternating sign matrix. And the way that you get it, the alternating sign matrix, is by doing this little recurrence that I was trying to explain. So the alternating sign matrix that goes with this kind of a quilt is just where Aij, the ij entry is defined to be the Fij minus Fij -1 minus Fi -1. Oh, that should be just a J. I'll fix that. And then plus the I -1, J -1. Oh, I love the magic of iPad. Okay, so do you see why this is true? This is a bit of a, takes a little bit of proof that every time that you do this, you're going to end up with an alternating sign matrix. And what it proves is that quilts, these CK cross CN quilts, are exactly in bijection with the K+1 by N+1 corner sum matrices. And those are exactly in bijection with the K times N alternating sign matrices. Okay, so that sort of saying these quilts are natural objects. And the reason that we call them ASM quilts, and after I go away from CK cross CN, is there still any connection at all with alternating sign matrices? And there is. And it's kind of like this. So if you have an arbitrary quilt for any P and Q posets, then every time you have a maximal chain in P and a maximal chain in Q, you can think about that as giving rise to a CK cross CN quilt, and therefore giving rise to an alternating sign matrix. And so there's a whole bunch of these alternating sign matrices running around all the time, and they're kind of interwoven in some way, right? Because of the way that the maximal chains will be interwoven in P and Q. So this is like the fabric of a quilt. Okay, so I did want to just step back for 1 second, because the alternating sign matrices are really important to us in the whole picture. So I want to make sure everybody is, if you haven't seen them before, you have a little introduction. Okay, so here's an aside on ASMs. So they're matrices that have zeros, ones, -1s. Each row and each column contains a 1. You can't have an all zeros row. And so it definitely contains a 1. And then the non-zero entries alternate. The leftmost non-zero row in each row is 1. The bottommost non-zero row in each column is a one. And then if k is less than or equal to n, the rightmost non-zero row has to also be a one. If k is bigger than n, then the topmost non-zero entry has to be a one. This is kind of to make the numerology work out right. And in the case where k equals n, then they have to both have both of those. So here's an example of a rectangular ASM, and this one, k is equal to 5, n is equal to 6, right? And the rightmost non-zero thing in each row is 1. So these were defined by Mills, Robbins, and Rumsey, who worked at CCR Princeton, so they're like a local object. Back in 1983. And they conjectured this beautiful formula for the number of square alternating sign matrices. This is exactly this very simple product. It's simple to compute, right? J equals 0 up to n minus 1, 3j plus 1 factorial divided by n plus j factorial. So it gives rise to the sequence 1, 2, 7, 42, 429, and so on. Definitely in the online encyclopedias of integer sequences. These are called the Robbins numbers. They were studying these things because it comes up when you study taking determinants of Dodgson condensation. And so they made this conjecture, and it is a theorem. This is really a big result in combinatorics, first proved by Dorn Zahlberger, 1996, and actually close in time by Greg Cooperberg in a somewhat slicker fashion. Is very beautiful. And then another proof by Ilse Fischer. So none of these proofs are easy. It's notoriously hard to prove. But there's no known geometric proof. So to answer the question from Math Overflow last night, there's lots of combinatorial identities that don't have a geometric proof, right? But if there was some way to prove this, it would be fascinating. So another thing to notice is that this is for the square case, and actually it's not known, and no nice formula is known if you do the rectangular case. So that's where we're at on those numbers. Okay, so here, since 1983, these alternating sign matrices have become very, very popular, and there's all kinds of different interpretations, combinatorial interpretations for them. So here's some examples. And notice that bumpless pipe dreams are among the list here, right? So Anna Wagen pointed this out after Lee and Shimizono gave their definition. So they're close to our heart in some sense. And there is a conference, in case some of you already know are experts in alternating sign matrices. If you haven't heard about it, there's going to be 42 years of ASM's conference in September in Ljubljana. That's where Matthias Kumbalinka, my collaborator, lives. So I hope you'll consider attending. But what are the key facts for us in terms of alternating sign matrices? So one of them is that all permutation matrices are alternating sign matrices, right? That's clear. But maybe more important is that Bruja order on permutations embeds into a lattice on the alternating sign matrices. This is a very interesting result. And you can think about it in terms of alternating sign matrices or in terms of these corner sum matrices. And the way that lattice works is just by comparing the corner sum matrices entry by entry. When you go up in this lattice. And it is actually the case that every one of those functions gives rise to some alternating sign matrix, right? We're using that fact. So Bruja order embeds in there nicely. And this lattice is the Dedekind McNeil completion of Bruja order. So the smallest possible lattice containing Bruja order. That's a result of Lesko and Schutzenberg. So those are some of the key pieces that we're using. All right. So inspired by the results on Bruja order and ASMs, we want to have some similar things with quilts. And so one of them is to say, okay, well, is there a poset running around here? And the poset, there's a very natural poset on quilts. Just we'll say that F is less than G if F of X, Y is less than G of X, Y for all pairs X and Y, and the product of the posets P, comma Q. Okay, that's easy enough. Certainly gives rise to some poset. It has the property of being a lattice as well. So there is a join and there is a meet. And the way that you get the join and the meet is the join is just to take the max of the two entries. The meet is just take the min of the two entries at every single point in P cross Q. But then what do you have to prove? We have to actually prove that that still gives rise to a quilt, right? It still has to have that Boolean growth property. But this works nicely because min and max work nicely. Okay, and then you actually also on this quilt lattice, you also have a unique minimal element F0 hat and a unique maximal element F1 hat. And you can sort of think about them intuitively. You know, what's the minimum? You're going to be 0 at the bottom as long as you possibly can until you have to, because of bounded growth start to go up, right? And that's what this function encodes. And then at the maximum is just like, you know, step up every time you can. In terms of the rank functions, you're going to step up every time. So just try and step up every time. The only thing is that, you know, at the top, the function will have to be the minimum of the ranks of the two posets. So every entry will be bounded by the rank in P and the rank in Q of that pair. Okay, so both of those exist. And then we're starting here now with the results in this paper. So this is with Matrices Kompolenka. We sort of summarize this in a theorem. So for every pair of finite ranked posets P and Q with a minimal and maximal element, then this poset on the quilts is a distributed lattice, has a unique minimal element, unique maximal element, and you can even say what the rank function is. And it's basically just sum up all the numbers in the quilt. It's kind of not quite right because that unique minimal element, well, you have to sum up the numbers in there. And that's not necessarily 0, so just shift down by that much. Okay, so that's the quilt rank. Easy enough, right? So this, to sketch the proof just a little bit, distributivity, if you haven't seen that in terms of posets or lattices before, that just means the meet and join distribute nicely. And why is that true? That's just because min and max also distribute nicely. So that's easy enough to see. But the quilt rank function is a little bit trickier. How do you know that for every quilt, if it's not maximal, there's at least one entry someplace in all of that mess where I can raise it up by 1 and it will still be a quilt. It won't violate some of the other conditions around above or below it, right? That's harder to see. And so in order to prove that, we considered a directed graph that kind of goes with this pair F and G. So we want to just compare 2 elements at a time and say, if I'm at F right now and I want to get to G, can I step up by just like 1 little bit? And G could be the maximal element, or it could just be anywhere in between. But if it's not the same as F, if G is different than F, there's definitely at least one place where some value X, Y, where they differ. And look at all of the vertices where F of X is strictly less than G of XY, sorry, F of XY is less than G of XY. So that's the difference set. And we want to put some edges on there to encode when the constraints exist that you can't bump up. So how do you do that? Well, that is a little bit of the trickiness in this. But the point is that we can impose these edges and we prove that this graph is acyclic. And since it's acyclic, it has a sink someplace. It's definitely not empty. It has a sink. And so a corollary is that we can tell you exactly, if you tell me the pair F and G and look at the interval between F and G, what are the atoms covering F? They are exactly in bijection with these sinks. The co-atoms, the ones that are 1 step down from G, they correspond with the sources. And so that's pretty easy. And the sinks and the sources are exactly pairs X, Y, where you can raise the value up by 1. So it's encoded in that. Okay, so that's nice. And this is kind of where we were hoping to get to. The quilts lattice on CK cross N, it encodes a whole bunch of these structures that we already talked about with rank functions. So it includes the lattice of alternating sign matrices. It includes matroids on a ground set 1 through N with rank K. And it has this kind of a poset on the matroids. You can just consider it as a subposet. It also, the quilts CK through VN also encode flag matroids, which wouldn't be a corresponding, like some different number of matroids all put together with, so that their rank functions have a coherence property also. And it encodes inside the quilts CK VN is the medium roast Fubini-Bruja order on spanning line configurations that motivated the problem with Pawlowski and Rhodes' work. So there's, there's something to this.
Is the poset that this induces on matroids like a well-studied poset?
So I think this is a well-known poset. Is it well-studied? I don't know a whole lot of results about that poset.
Okay.
In terms of like, what are the covering relations? What is the Morvis function? So, but it does give us some ways of attacking these problems. And one of the open problems still with the medium roast Fubini-Bruja order is how exactly do you get the covering relations? They're tricky, but this at least is embedded it in this nice lattice and can help. Here's the problem. So even if you look at quilts C2 cross P3, there's 199 of them. So the Hausel diagram looks like this little hurricane here. And all these nice objects that we have, like the alternating sign matrices of size 2 by 3, well, there's 7 of them. And the Fubini words of length 3 with on numbers from 1 and 2, there's 6 of them, and on number of matroids on 1 through 3 of rank 2, well, there's 7 of them. And they're kind of sparsely populating this 199, right? This is just a small case. So we tried to indicate they're somewhat overlapping. So using colors and shapes, you can identify them in this picture. So there's a lot of extra stuff, right?
You choose different maximal chains in B3, do you get different copies of ASM?
Oh, yeah. Sure. Well, this one was, yeah, so this is just with, I guess with one choice, yes. With
You still don't get all.
the most natural chain, 0, 1, 2, 3. You get all of them, I mean, they're all in there.
And if you choose a different chain, you would get a different image.
Right, okay, so you've got a lot of different ways of doing that.
Karen?
Yes.
How about distributed lattice? This is the lattice of order ideals of some posets. Do you know what that poset is?
No, that's a good question. Yeah, we don't really know. Nathan Reading was already asking about that too, and trying to study it a little bit. It's a good question.
Following that, there's a polytope. Is the answer the same?
Actually, a question about polytopes is definitely open. I don't really understand sort of how to do this with polytopes either. But we do have, what we're claiming here is at least this covers the cases of ranks that we've seen before, also the ranks of posets, also the ranks of graphs. So if you're friendly with rank functions, then these hopefully generalize your favorite kind of rank. All right, so here we go into the enumeration part, though. They're motivated by geometry, but then you get there, you made this new thing, and now what can you do with it, right? And we were interested in seeing what we could count and what we can't count with this. Since mostly probably inspired by the fact that the alternating sign matrices have such interesting enumeration, but these are hard. So the computing the number of quilts for an arbitrary pair of posets P and Q is definitely sharp P complete in the size of P cross Q. And here we're thinking about sharp P complete in Igor Pak's way. So in the sense that if I hand you a quilt, there is clearly a polynomial time algorithm to check if that function actually satisfies the boundary conditions and the Boolean growth property. That's not too hard. So that would imply it's in sharp P. And conversely, we're reduced to the problem of counting anti-chains in a poset. So this was known to be sharp P complete by Provan and Ball, 1983, I think that is. And so how do you do that? Well, if you look at the quilts of P comma C1, just a chain with 2 elements, right? Then it embeds into the anti-chains of the poset by considering your quilt and take the set of all elements X in P where f of x comma 1 is actually 1 and not 0. Take the minimal elements of that, and it's going to have to be a anti-chain. So which anti-chains get hit by this inclusion? Well, it'll be everything except if you take the empty set, that would mean a quilt where all the values were 1, but that's not allowed because we have the boundary conditions has to be 0 at the bottom. And also you can't have the 1 element anti-chain, which is just 0, because that would also imply that you have a 1 at the bottom. So those two are the only ones that don't get hit, otherwise it's just and in which case counting anti-chains is at least as hard as counting quilts in P comma Q for an arbitrary Q. So this implies Sharpie complete. Okay, so great. Well, that's hard, but maybe there's some special cases, right, where you can get somewhere. And the special cases that we consider are related to the 3 posets that we talked about: anti-chain quilts, Boolean, lattices, and chains. So let's start off with an example where you have any poset crossed with an anti-chain poset. Okay, and so here's an example. Actually, what kind of type of quilt is this? Do you see what are the 2 posets being product together there? Yeah. So A4 crossed with an A3. Right, so that's an anti-chain quilt. And well, you can, in polynomial time, you can verify that these numbers are actually doing the right thing, right? All 0 at the bottoms. And then you have to compare this one with this one and up here. But really for anti-chain quilts, the reason this is nice is because you're basically, you have to go from 0 to 2, right? Because the rank of A2 is 2. And so it's really about picking out the subsets where the 1s are going to go. So you can see the enumeration is going to be somewhat exponential. Right? Okay, so I can't do much about that except have you write down the formula. And here's the theorem. And that is, as long as P actually is rank 2 or higher, then the number of quilts P crossed with A2J is always going to be the sum over some subset of special convex cut sets, and then this number alpha PC to the J. So let me tell you what the definitions mean there, but a sum of powers of numbers, and they depend on the poset. So here, convex cut sets. Convex just means if you have a pair of elements in C, then the whole entire interval between X and Y are also in C. That's a sort of convexity. A cut set means that every maximal chain in P going from the 0 to the 1 always has to contain at least one element that is in this cut set. So if you took it away, it would be cut. And alpha P of C is the number of antichains in C as a subposet of P. Okay, so that's easy enough to define. Not only finding antichains, we know it's hard, but so easy enough to describe. And now you plug this into the formula. The worst case scenario is the cut set where you take out everything in P except the 0 and the 1. And in that case, the number of antichains is almost the number of antichains itself, but -2 there for the empty set and the 0. And these we actually sort of want to need numbers like this. So this number of antichains -2, we'll call this D1 of P. And this generalizes the Dedekind numbers. I'll come back to Dedekind numbers in a second if you don't know them. But the corollary here is that asymptotically, the number of quilts of these anti-chain quilts is always going to be this Dedekind number to the jth power. So at least the asymptotics are clear. Okay, so Dedekind numbers. How many of you know what a Dedekind number is? Good, I have something to tell you. Good. I think I've been fascinated by these for over a decade. Svante Linnaeus told me about these related to building theory, actually. And so the Dedekind numbers were an early addition to Neil Sloan's online encyclopedia of integer sequences before it was online, on an index card someplace. And but they're extremely hard to count. They just are the number of antichains in the Boolean lattice, right? Which is a very natural thing. But the 9th Dedekind number was just calculated 2 years ago, believe it or not. And it's huge, it's absolutely huge, and that is like 20 years after the 8th Dedekind number was calculated, so a huge gap. And now you might, this is done by Jackal, and you might even say, well, how do you know you got it right? Right, if it's that hard to compute. But luckily, in the same year, another team actually came up with it, which is amazing coincidence that it was in the same year, but they came up with the same number. So I'm fairly convinced they got it right. Now, yeah.
Was there a major technological advance that sort of made it?
Yeah, well, they're taking advantage of some of the symmetry. It is somewhat about the hardware and GPUs and things, that they can do things that you wouldn't have to parallelize. It is parallelizable, but they talk a lot about how they did the computation in these papers. Because really, that's all there is to report, right? Otherwise, it's just, here's the number. Okay, so the 10th Dedekind number, it's open for you. Or ChatGPT, maybe we should ask. I haven't tried that. Okay, so. Okay, this is saying, you know, the asymptotics are still hard. But at least it's a relationship. And a nice corollary that comes out of our theorem for the anti-chain posets is if you're in the special case where you're counting quilts CK crossed with A2J, at least there is nice because the number of anti-chains in cut sets for CK is easy to figure out. And so we get this nice formula. The sum I goes from 2 up to K of the numbers K plus 1 minus I quantity times I to the power J. And it, you know, how does that go in terms of J and how does that go in terms of K? You can think about that. Here's an example. So quilts 4, C4 crossed with A2 to the J. So how does it go with J? Well, it's going to be 3 times 2 to the J plus 2 times 3 to the J plus 4 to the J. Why is that? Because you're just counting these cut sets, right? The C4 has 5 elements. So really the only relevant stuff is in the middle because you know it has to be at the bottom and the top. And so in the middle here, well, you have 3 singletons. You have 2 cut sets that are convex. You can't take the 2 outer ones. That wouldn't be convex. And, or all 3 at once. Okay, so that's easy. And then how does it go with K? Let's say J is fixed to be 3, then well, if J, no matter what J is, if you fix J, this formula is going to be a sum. It's polynomial in K. You've got K is appearing in the sum, but it is a sum that also goes up to K. And so it's when J is equal to 3, let's say that will end up being like a sum of things that are like 4th powers. So when you sum, it'll be like a 5th power kind of thing. And K here is the exact polynomial. And those denominators, they're Bernoulli numbers, which Chris mentioned with a little sadness, but I always say, hey, there's Bernoulli. But that's just what you get whenever you're expanding powers. Like a sum I to the power going from 1 to K. Okay, so some results are obtainable out of this theorem. And another special case that we studied are the chain quilts. So I said these are kind of nice, right? You take an arbitrary poset crossed with a chain, and then all of the quilts are going to just be like on every single entry in the poset. In the Hasse diagram, you're going to have a little sequence of increasing numbers that satisfy the Boolean growth in the right ways. And in this case, for any poset whatsoever, the number of quilts of type P, CN, it's always going to be a polynomial in N as N gets large, as long as N is bigger than the rank of K. Before that, you get a little bit of stunting, but as long as N is big enough, these are going to be polynomial. The best way to expand this as a polynomial is in terms of the N choose M basis, not the usual N to the M basis. And the coefficients in this case are going to be something which we're going to call the M fundamental quilts for P. I'm kind of thinking about them like fundamental quasi-symmetric functions. And the ones where you use all of the possible numbers will be the standard ones. And that will give you the asymptotics, the biggest ones. So S of P will be the standard quilts. And I want to define them for you. I may, but the biggest terms will be what determines the asymptotics.
You,
So,
you get a new formula for it.
that's coming as a corollary, yeah. We're pretty excited about that, actually. So B of P, what is that? That's a natural statistic that should be associated to every poset. And it's just sum up all the ranks in the poset. Everything is ranked anyway, so it has a rank function. So that's gonna be sort of our big number. And then the M fundamental chain quilts associated to P. It doesn't matter which CN you're crossing it with. This is just goes with P. But let me give you an example. I have to sort of fix a little bit of notation before I can do it. So let's look at the example of B3 cross C5. Okay. I could give you an example of a quilt by listing out these lots of numbers, but you can see as N gets large, these sequences are going to get hard for me to write them all down like this. But what really matters again is the jump sets. Right, so we're pretty familiar with that. So, okay, so just notice the jump sets. And then for every X in the poset, your jump set corresponding to a quilt will be the set of all indices I such that F of X cross comma I is strictly bigger than F of X comma I minus 1. Right, so it has strictly bigger means it jumps up by 1. And so we'll call this the monotone triangle form because back in alternating sign matrix land, there is an analogous picture called monotone triangles. And that's what we're doing here. And a little lemma that you have to check is that every time you have one of these chain quilts, if you have X covered by Y, how do their jump sets compare? Well, they have to be interlacing because of this alternating sign matrix property. So interlacing here means that if I called the jump set for X, X1, X2 up through some XP, and the one for Y, let's call it Y1 through YP, it has to be the case that you have X1 is smaller than Y1 is less than X2 is less than the next one. They alternate back and forth. So kind of little zigzag as you go through. And then the other cases, one of them could be longer than the other, but only by 1. Basically, this alternating property. On the right-hand side, I have a little example of an actual monotone triangle. And that's what they look like. This would be a 3-row one. And you can have, so the top row interlaces the second row, and the second row interlaces the third row, and so on. Okay, so we have these interlacing properties for every pair of coverlet relations. And those completely determine the quilts too. So I could have defined quilts of these chain quilts in terms of these interlacing properties on the right instead. Be absolutely equivalent. So now the definition is a chain quilt is M fundamental if its monotone triangle form contains exactly the values 1, 2, 3, 4, all the way up to M. Has to include all of them to be fundamental. Okay, and then here are all of the fundamental quilts for B2. So the first 4 of them only use the numbers 1 and 2. The next group of 5 of them use the numbers 1, 2, and 3, and the last group use the numbers 1, 2, 3, and 4. And the ones that use as many numbers as possible are the standard quilts. And how many numbers is as many as possible? Well, that is actually 1 up to B of P, that statistic. So the standard quilts are the B of P fundamental quilts. Okay, great. So from this data, then you can compute what is the number of quilts of B2, comma Cn for all n, and it's going to be this polynomial in n. The 4 fundamental quilts for m equals 2, the 5 for m equals 3, the 2 for m equals 4. And of course, asymptotically, the biggest term will be the fundamental or the standard quilt. So that's how it's like 2 times n to the 4th, or 4 factorial. So n to the 4th over 12. Okay, and for B3, Cn, you can figure that out too, but already the number of standard quilts is 1,344. You know, you don't do that by hand, right? Right, so they get big fast, but it would be very interesting to understand the number of standard quilts for a poset in a better way. Like, just like we understand the number of standard tableau, it'd be really neat if there's some kind of a formula like that. So I wanted to explain them a little to you, hoping somebody's gonna catch on to this idea. We don't have a formula for that though. And then an even more special case would be when you take the product of two chains, right? And then we're back into the world of ASMs. And what is the B of P number in that case? What's B of P when P is a chain? Well, it's just sum of all the ranks in this chain, right? So that's just the sum of the numbers from 1 to K. So K plus 1 choose 2 is B of P here. And the monotone triangle form in this case really is going to be a monotone triangle back in the ASM case. So let's say if we take K equals to 3, in which case 4 choose 2 is 6. Monotone triangles will be 3 rows tall. They'll use the numbers from 1 to 6 if they're going to be standard. And how many different ones are there? Well, here's one, for example. So 1, 3, 6 across the top, 2, 5, and 4. What else can I do? I sort of have to have the 1 and the 6 on the top row be interlacing. Do you see any other options?
So 3 and 4.
Yeah. 4 here, 2, 5, 3. You have to have this long chain of 5 increasing things if you go down and then up again, right? So you just don't have a lot of choices here. So these are the only ones, these two. So the standard
Whoa.
the standard quilts for CK biject to shifted standard tableau of staircase shape, K rows. And in which case there is actually a hook length formula that's already in Thrall's paper. So so we at least know now the asymptotics of the rectangular ASMs from this. You know, so there's some nice coefficient easily computable, and then into the K plus 1 choose 2. So we believe this is new in the world of ASMs. Yeah. Still leaves a lot of terms left in the polynomial. Or,
Some more work to do.
yeah, more work for all of you. Add to your list. Okay, and then just to complete the package, right, we're looking at anti-chain quilts, chain quilts. What about Boolean quilts? So you take P cross a Boolean lattice, and those are going to be a lot harder. All we have right now are asymptotics for those numbers. They come from the asymptotics of Dedekind numbers to some extent. And so they're bounded by something like 2 to the n choose floor of n over 2, which is a pretty bad number to choose. They're big, and the upper bound is similar, but a little bit worse and has a B, a P, and an exponent there. So they're growing very fast, but we have some asymptotics. And if we could understand the Dedekind numbers, these would improve the asymptotics. But since those are kind of wildly difficult, we don't know a lot. Okay, and this is good. I wanted to share some open problems to get back to the geometry with you. And back to the geometry and back to the matrices, I also think this is the right group to advertise this problem. You know, it's an interesting question of if you have a matroid, is it representable? Right, and that's well understood, just, I believe. What happens here? What happens if I give you a quilt of type BK cross BN? Could you tell whether or not there actually is a matrix so that this is the rank function for all subsets of rows and subsets of columns? Right, that's right now completely hard for me to see if that, how to produce such a matrix. To see how hard this might be, even when K equals N equals 2, how many different representable functions quilts will there be? Well, there'll be 7 of them. They correspond to the identity and its rotation, the 1, 1, 1, 0, 1 and its 4 rotations. So there's 2 of this type, 4 of that type, and then 1 more. Those are the 7 representable ones. There are 199 total. So most are not representable, but how do you put a firm test on that?
Do you think this is computable?
Yeah, I mean, I do, yeah, I think it is. I think that there's got to be some way to say in terms of these generalized rank functions.
Isn't like the matroid question? It's not, right? It's hopeless for matroid.
Right,
You think it's
The
hopeless?
second step is hopeless, but like, when did it come from a bimatroid? That's probably doable.
I don't think anything's hopeless. Much more. But this is gonna be a hard problem, but I think it would be interesting. A bimatroid's a good idea though, actually, yeah.
Yeah, I think bimatroids work, but not representability for bimatroids is really hard, so.
Okay, so at least it's a well-defined problem. And then here's where I'm very interested in seeing, okay, it's a related question, but maybe a little easier, I'm not sure, but CK cross BN. This would be like flag matroid, where the flag, where you have some matroid for all of the ranks 1 through K. And so I'd like to understand, when is there a K by N matrix so that these ranks come from looking at the top so many rows and any subset of columns. And those contain the, they're closely related to these Pawlowski-Rhodes cells in the span-long configurations. And the medium Roche-Fubini-Bruja order can be described in terms of these functions. Exactly, the relationship between them is exactly from the quilt lattice. And so when do those kind of functions come from? K by N matrices that are full rank and have no zero columns. Those would be the special ones that go with this. Okay, so that's another realizability question that again seems kind of, this does seem hard. And then, you know, in terms of plenty to do, there's so many beautiful things on alternating sign matrices, you can try and generalize all of them. Well, in particular, there are these beautiful alternating sign matrix varieties, and we're going to study. And so are there quilt varieties, or are there quilt polytopes that you can do with alternating sign matrices? You can ask if you can do it here more generally. And you can also try and generalize some of the algebraic or combinatorial properties. And I wanted to give a shout out to Zach Hamaker and Vic Reiner in this paper, that they were studying alternating sign matrices and have some analog of descents. So is there an idea for descents in quilts? Or are there, we have this lattice quilts PQ, does it correspond to a shellable poset? And is there Huff algebra interpretations or building on what you guys have done? Those were all interesting questions that I think they follow nicely from this work. So thanks for listening.
Any questions?
Federico?
Way over there.
Okay.
Steven.
Oh, yeah, so I know you and Matthias thought about double cosets, this next but parallels.
Yeah.
Is that possibly connected if you replace Boolean growth by instead of going up by at most 1, you go up by some bigger number depending on the edge?
Yeah, actually, that's interesting because other people have studied some other kinds of jumps like that where you go up by at most something. We found that these were much more controllable and more readily countable. But I haven't thought about trying to connect that to the double cosets. That's good. That's a good idea.
Sarah, so one thing that I really like about this story is that when I look at the definition behind you, I don't see an alternating sign matrix, right? It kind of doesn't surprise that it appears. Many, many years ago, you and I looked at these kind of 3D versions of this, where you're coming from Schubert calculus of the flag variety, and I was curious if you also get some kind of 3D object that's like an alternating sign matrix.
And Minkowski sums of something to get pieces and stuff and tiling. That's a very interesting, maybe that's a really good idea. Like, you know, alternating sign matrices and tilings and things go hand in hand. So how do you do that with quilts? That's another one we should add to this. That's really good. Yeah.
What are some, you said generalize the polytope story, but can you remind us what's the classical story about polytopes in ASM?
Yeah. So, you know, like Chris was talking about, you have polytopes that come from subsets, right? You can also look at polytopes that come from things that have signed sets, and they're related to these ASM polytopes. I haven't studied them so much. So we have some papers that we recommend you look at to generalize them in our paper. I have not tried anything to think about these polytopes in more general. 100.
So ASMs would be like nice limiting behaviors. Is for any particular example, like the anti-chain or the Boolean, how does a random quilt look like?
Yeah, what does a random quilt look like? That's a really good idea too, but, I don't have the best way of representing P cross Q maybe necessarily. But I guess in certain cases, right, that's a good question, right? We can do this for CK cross the N. So where else does it look reasonably nice? Maybe the anti-chain cross chain would be a good place to look. I am much more interested though in the CK cross BN, and that one just gets messy so fast and been able to make a nice picture.
Are there non-Q analogs or geometric size? So for example, in ASM, you say there's a rank function that can come from matrix. So what if say you count the number of matrices over finite field that give you a given data?
Ooh. Ooh, that's a really good idea. I didn't think to do anything like that. Yeah. So if you just take matrices over FQ, how are the quilts, I guess, realizable quilts growing? And then you're thinking like BK cross BN. Yeah. And is that a polynomial? I guess would be the question. Crazy. Yeah, I like that. I'm afraid it might not be polynomial, right? Because
But then the more so I think the CK cross CK thing, they have this formula. So like that will hint that might be a Q hypergeometric version.
Yeah.
But then you need to say that you need to find some space so that the Euler characteristic of that is equal to that.
Yeah. Yeah.
For the, I guess, lower order terms on your quilts, would they not just be sort of plain partitions on the shifted staircase with
So for
that, I guess, what do they call it? Like
alternating sign matrices, you mean CK cross CN kind of thing?
for the, well, specifically you have the like B of a chain, but then you have the lower order terms. Are they not going to correspond? Would they just correspond to shifted plane partitions where the entries are all values between 1 and say K, or 1 and say A less than?
For some reason, I thought the inequalities didn't work up quite right.
Okay. It's only when you have.
You can, yeah, you have to kind of twist your head to look like this.
Okay.
Yeah, that's why I think it broke there, but.
Right.
David.
In the spirit of Chris's, what about type D? Do you look at like, there's ASMs with symmetry, they're like wonderful enumerations of like symmetric partitions.
No, didn't look at that either, or isotropic line configurations either.
What about 5G2?
Is there a intent
So I
to
it's not what
matrices?
type D, you do some folding.
Yeah, oh, that's interesting. Take some folding about it. Yeah.
Aren't there?
We're recording these questions, right?
All right, well, let's thank Sara again.